Yeah, I have started. Yeah, it will be starting. Okay, we are live. Yeah.
You're live now?
Yes, we should wait for 30 seconds.
Hi, good evening, good morning, good night, good day, whatever parts of the world you are. We are going to have the first keynote talk of the conference. Just wait for a few minutes before we introduce the speaker. This is Ashutosh Datta. We just wait to have the attendees join. We'll start in next 20 seconds. Raj, you can just let me know when it's time.
I think we can go ahead. Yeah.
Yeah, Ashutosh, I don't see Raj. Yeah, please go ahead, I think.
Okay, excellent. So good morning, good day, good evening. Again, attendees of COMSNETS, 13th COMSNET 2021. Ashutosh Datta, one of the general co-chair. I also have other co-chairs and steering committee on board with Ranjita Bhagwan and Manish Gupta. I have the distinct pleasure of introducing our first conference keynote speaker, Professor Michele Zorzi from University of Padua in Italy, and he'll be speaking about understanding the potential challenges of 5G mmWave technologies for public safety networks. This is so important, in fact, very close to my heart as well, to understand how 5G and beyond 5G is going to be useful to public safety fast responder community. So my distinct pleasure to introduce Professor Zorzi, who is, first of all, is an IEEE fellow. At the same time, he's a IEEE Communication Society's leader and Board of Governor member as well. I know him almost 20 years, maybe more than 20 years, 1999 when I first met him. In fact, I visited his institute as well, University of Padua. He's a professor there. He also had faculty appointment with University of California, San Diego, UCSD, at various points of time. His main research interest, obviously, in the communication systems, 5G mmWave, cellular, energy constant communication protocols, ad hoc and sensor networks. He has done many roles as a IEEE leader, and many of them towards the magazines. He was the editor-in-chief of IEEE Wireless Communications, editor-in-chief from Transaction Communication 2008 to 2011. He also founded the IEEE Transactions of Cognitive Communication Networks. In addition to that, he's been guest editor for many spatial issues in personal communication, wireless communication, IEEE network, and IEEE journal on selected area communications. As I said, he right now serving in the Board of Governor. In the past, he was also a member at large, 2009 to 2011. In addition to that, he has served as Director of Education Training 2014 to 15. Because of that, actually, he also won the Education Award in 2016. Currently, he's actually a Director of Journals, serving as Director of Journals. He had many awards, including the Best Tutorial Paper Award 2008, 2019, the Stephen Rice Best Paper Award 2018, and Education Award 2016. So with that, Professor Zorzi, I will hand it over to you. And people who are have questions, please put your questions in the Q&A box, and after the talk, we'll have the opportunity to ask the keynote speaker about the questions. With that, Professor Zorzi, I'll hand it over to you. Let me stop sharing. So Professor Georgi, you can now share your screen. And another reminder, we are going to take the question answer towards the end, but during the presentation, if attendees have any question, please put that in the Q&A chat box. It's coming up. I can see the screen image. Just maximize. Yes, thank you.
Okay, so you can see it now?
Yes.
Okay.
We can see you, we can hear you. Yeah, please.
Okay then. So we're good to go. Okay, so hi everyone. Let me start by thanking my good friend Ashutosh and also the rest of the organizing team for inviting me to deliver this talk on the challenges and potentials of 5G millimeter wave technology for public safety networks. So this work or this presentation is the result of many research activities that were carried out with many collaborators, of course, my own students or former students listed here, Michele Polese, Marco Giordani, Tommaso Zugno, Matteo Drago, and also colleagues from NYU Wireless. And in fact, with them, we had a 3-year project supported by the US National Institute of Standards and Technology under a federal award for 3 years, which recently ended. And so this and that project was exactly on using millimeter wave for public safety applications. Let me see if I can improve my pointer here. Here, okay. Okay, so public safety. Why do we even talk about this? Now, this may seem kind of obvious, but I think it's good to just go through it to establish some common ground. So we have first responders, people who are on the field, and they need to communicate in case of emergency. So where does this need come from? Well, of course, you have several people in the field, and they need to share information. Obviously, having a broader point of view and letting other people know what you are seeing or what you are experiencing through sensors will have a potentially very high value, because in some situations, this may even be life-saving information. And in any case, it will allow people to have a common view of what is happening and to be more effective in responding to whatever situation they're facing. Another important action is to gather intelligence. So once again, having a common view and complete view of the scene will be key in being able to make good decisions. And so we assume that besides the people on the field, we may have some command and control center where the information they gather on the field will be uploaded. And based on all this complete information, the command and control center may actually make decisions and communicate or give orders to people who are on the scene. And so sharing information is more like a peer-to-peer kind of task. Gathering intelligence is more like an upload or upstream type of action. And then, of course, as a consequence, we have downstream actions down here. So we may have equipment that we need to control remotely. So, for example, we may have drones flying or robots going into the scene, and they need to be controlled remotely. And so this will need a reliable link for that, and also transmit orders to the actual responders and let them know what they need to do to operate in a fashion. And clearly, as this information is critical, and sometimes things happen very quickly, you will need a very reliable link with very high performance in terms of both throughput and delay and reliability and all that. Now, I mentioned the project that we had with New York University as the prime leader and the University of Padova, and also another partner of the project was the fire department of Austin, Texas. And so with them, during the project, we actually came up with real scenarios coming from their experience. And so this picture shows one such possibility where you can find the elements I was mentioning while talking in the slide before. So we have some disastrous scene, which in this case is a fire. Then we have responders on the field, which in this case are firefighters. Then we have a command and control system here on the left where decisions are made. And then we have sensors, some of which may be with the responders, so they can wear cameras or various sensors on their body or their helmet. And also we have, in this case, drones that fly over the scene and collect information from above. And so all this information is delivered to the command and control station, decisions are made, and they are fed back to the people on the field, including, in this case, there is a fire truck here, but other types of equipment can also be envisioned. Now, clearly, this is a very relevant scenario, not only for the Austin Fire Department, but even for the population at large. These scenarios are becoming very important. Now, you may have seen what happened in California a couple of months back, where there were huge fires. There's an estimate that in 2018, these fires caused damages up to $12 billion. In some cases, they actually may have been casualties, and many homes were destroyed. And so this is a very important issue for the whole population. So being able to intervene quickly and effectively is, of course, very important to minimize the damage that these fires can make. So this is all very well, but if you look at how things are today, currently this scenario is actually not well supported, because typical systems that are used here in public safety scenarios, they were originally designed for very reliable voice communication, because the responders need to talk to each other and try to coordinate a little bit. But these more advanced type of services, like collecting data, taking pictures, taking videos, or even having a virtual reality, augmented reality type of vision that allows responders to see things that they're not in front of necessarily. All of this requires orders of magnitude more capabilities than were currently envisioned in these communication systems. And so here we have a mismatch between a clear vision of how you can make this type of action very effective and very coordinated, and the reality of communication systems that fall short of the requirements that are needed in these kind of scenarios to provide these kinds of capabilities. And clearly, as I said before, this has to do mainly with the data rates that are not up to what would be needed to support high quality video or virtual reality, augmented reality, and also latency requirements that may be very stringent here. And so since both our group and the group at NYU with whom we collaborated a lot in the past few years, we both came from research on millimeter wave wireless, where the key advantage is the availability of very large bandwidth, and so the availability of potentially very high data rates and very low latencies, we said, why not trying to understand how we can play this technology into this scenario to enable this kind of applications. And so that was the basic idea behind the project that we proposed to NIST and got funded. And the paper that's mentioned at the bottom of this slide gives you an overview of the project, the vision, and type of scenarios we addressed in this project. So I tried to put at the bottom of some slides some references mostly to our own work where you can find more information about what's shown in the slide and briefly talked about by me. And clearly, if you have any interest in any of these topics, you can find a lot more in these papers. And also, I assume that the organizers can make this presentation available. I'll let them have the slides so they can share them freely with whoever is interested. So mmWaves, so 3GPP, which is the standardization body for cellular systems, have issued or issues releases of their standard every so many months, and recently has released release 15 for 5G, where NR was defined. NR is the new radio interface for 5G, which, among other things, supports frequencies up to 52.6 gigahertz, so well beyond the traditional frequencies used for cellular communications, which are, in this region here, up to 2-3 gigahertz, or typically the boundary. I mean, the boundary is not very precise here, but sometimes we divide between sub 6 gigahertz and above 6 gigahertz, so that practically is the boundary between traditional frequencies that we use in LTE or also traditional Wi-Fi networks, and what's in the mmWave spectrum, which technically would start at 30 gigahertz. I mean, by definition, in physics, the 30 gigahertz of frequency corresponds to a millimeter of wavelength, but loosely defined, this includes also some frequencies below 30 gigahertz down to, as I said, about 6. Now, the main advantage of having this band available is that, unlike in the crowded spectrum down here, well, there is a whole lot more spectrum and also many available gaps that can be used or can be assigned to systems. And so now we have the possibility of assigning hundreds of megahertz or even gigahertz of bandwidth, which is, of course, unthinkable in current systems. And so that translates immediately in a huge improvement or increase in the data rates that are potentially achievable. And so, for example, if 1 gigabit per second for peak rate was the desired requirement for 4G, then we can hope for up to maybe 20 gigabits per second of peak rate in 5G using mmWave. And if the latency in LTE was in the order of 10 or tens of milliseconds, we can hope that this can go down to 1 millisecond or less. That guarantees, the type of interactivity we were talking about in the previous slides. And so this type of features seem to be well matched to what we were describing earlier in terms of the type of scenarios we would like to address and the type of services and applications we would like to implement in such a scenario, including wireless VR, AR to first responders, remote monitoring for equipment that is in the field, and also vehicular communications, machine type communications, and so on. Now, the spectrum at millimeter waves comes with its own challenges. So this picture, which you may have seen, shows the attenuation in dB per kilometer that is due to the frequency. Of course, attenuation has several components. We have a component that depends on distance, and then a fixed component on top of that depends on frequency. And you can see that in some frequency ranges, there are good properties, like these green circles I'm showing here, so that you have some minima of the attenuation you have. So these are clearly good bands to be used for communication, whereas there are peaks where because of some physical phenomena like oxygen absorption, for example, at 60 gigahertz, you have very high attenuation, which, while being a problem from our point of view, where we want to implement a good system that is able to carry information across decent distances, this may actually become an advantage if you want to protect your signal, or if you want to confine your signal to reduce interference, as, for example, in WiGig, which is the version of Wi-Fi at 60 gigahertz, which uses this band, which seems like a strange choice because of this unfavorable propagation condition, but this actually guarantees that signals are confined into small spaces, and so you can replicate or you can reduce interference. And so this explains a little bit why this is done. Okay, so clearly this also shows why current systems work down here, because here is the best response here in terms of attenuation as a function of frequency. But if you want to go up, you have to face this type of problems, and you have to position in the good bands and account for the fact that since we have more attenuation at these frequencies, we need to find ways to compensate for that. So one way of doing that, of compensating for the increased path loss or attenuation compared to traditional systems, is by using antenna arrays. So one device that actually is being used at NYU for experiments. So one good thing about millimeter waves is that the wavelength is very small, and so you can implement this kind of antenna arrays in a small form factor. So you can see that this is shows you the comparison between a coin and the size of the device, and you see that the antenna elements here are separated by distances of the order of millimeters, which is how it should be, right? Because the separation between antenna elements typically is of the same order of the wavelength, and so having millimeter as the unit makes this very compact, which you can't at frequencies like 1 gigahertz or below, where of course this would be much larger. And so high frequency means more difficult propagation environment, but also the opportunity to pack many antennas, which compensates for that kind of difficulty. So this is good, right? Because you have this opportunity, even though, of course, using beamforming very, very massively means that you need a lot of signal processing to go into the devices, and also you need to maintain alignment, which will require some sort of overhead or signaling, beam tracking type of techniques, which, however, have been subject to a lot of research recently. And so these are problems that people are solving. Now, the other problem with the millimeter waves is that, again, due to the small wavelength, we have significant effects in terms of reflections and diffraction, but also in terms of blockage. So objects that are almost transparent to more traditional frequencies in the sub-6 gigahertz band become completely blocking at these millimeter wave frequencies. So you may have where, this is, I believe it's downtown Bristol. So there is some kind of path that a mobile is moving along. And this is, as a function of the position, what is the quality of the signal received. And you can see that we have times where we have line of sight communication, which is good. So you have a good quality of the signal. Then we can have non-line of sight. For example, if there is something in between that interferes with the signal, and so you get much less signal power. Or if this becomes really bad, for example, you're, let's say, behind a building, then you may be in complete outage where your signal quality is so low that you cannot communicate. But then very quickly you may actually recover and go back to line of sight according to where you are with respect to your access point. In this picture in the middle here, you can see this is a downtown area that shows several base stations, and so the color shows the signal intensity. And so clearly, where orange are the main beams here, yellow is a little bit less, and green is even less here, and similarly to the right here. So planning and trying to guarantee good coverage is challenging here, and needs this technology needs maybe densification of the network, it needs beamforming, but these are all things that are being done, and so this type of scenarios are being rolled out. So this is what happens in general in millimeter wave. Now, in public safety, we have even additional challenges. So those challenges will be there for public safety as well, even though maybe we may not be necessarily in a city environment. But these issues about propagation and attenuation and beamforming will be there as well. In public safety, we may have additional things like we expect to make good use of flying nodes, UAVs, so unmanned aerial vehicles, or vehicular communications on the ground. So, for example, the channel between a flying object and the ground is not well characterized, so we don't have good models for these. We don't have much experience with the three-dimensional management of objects and three-dimensional networks, which will be what you have. You have a flying object at different altitudes. You may need sophisticated tracking because clearly, one thing is someone walking in some scene. Another thing is a drone flying more quickly and in 3 dimensions. And so this will need new algorithms to enable a good tracking and management of this type of nodes. Another challenge that is not there necessarily in more traditional cellular systems is ad hoc deployments and resilient deployments. Clearly, we are looking at scenarios where the infrastructure may be compromised, and so you have to put together some infrastructure ad hoc in hostile environments where maybe there is still fire, there is smoke, there's dangerous situations where nodes may need to move, and so you need networks that are able to adapt to these situations and still provide a good communication infrastructure, even in the face of all these changes and dynamics and these difficulties. And also, if you have mobile nodes or flying nodes that try to mimic some cellular system, now you don't have the luxury that you have when you design a cellular system to carefully position your base stations, but you have to do with what you have. Okay, and so while there is room for optimization, clearly the situation here is much more challenging than it was in traditional systems. And if we have unmanned nodes, we may need to implement machine type communications also in mmWave, which is something that is relatively unexplored as of now. So we addressed several different topics in this project. So one of these was how to enable public safety using a three-dimensional coverage by complementing, or in some cases even replacing, if the terrestrial infrastructure is completely compromised, with non-terrestrial elements, which include anything that's not on the ground. So they can be as simple as drones flying at a few meters or tens of meters. They can be high altitude platforms. They can be satellites with different constellations, from low Earth orbit satellites at a few hundred kilometers from the Earth, all the way up to geostationary satellites at 36,000 kilometers of altitude. Okay? And the reason why this is attractive, I'm trying to use these cartoons here to show what you can do with this. Now, clearly, these nodes have an excellent broadcasting capability. And so these are very good to send information over an area without an infrastructure. They can do relaying. They can serve a relatively large area, potentially, but focus their service only on some part of it. So if there is an area which needs bandwidth at a certain time, it's possible to just configure your beam, your antenna on the satellite, to illuminate that sub area where you need communication at that time, or where you need additional bandwidth because maybe that's more crowded areas. There are more responders there because that's the hottest point in the scene, and so you can easily manage this dynamically, which of course would be very difficult with the terrestrial infrastructure. You may even implement in these flying nodes a mobile edge cloud type of services with some processing, some intelligence that can provide services beyond the simple pure connectivity that we talked about so far. And then if we look at these non-terrestrial networks in a broad way, then we can identify different layers of non-terrestrial nodes. As I mentioned earlier, you can have drones, features in terms of coverage, in terms of capabilities. Then we can have satellites that have completely different capabilities in terms of area served and requirements or capabilities. And you can integrate this all together into a heterogeneous type of network structure, which can then be used dynamically and opportunistically, if you wish, to get the best service out of each layer according to the needs of the nodes that need to be served. Okay, and so there are many good opportunities here, but of course, for example, this last case I was discussing, managing this heterogeneous network becomes challenging, right? And so we have good potential and good opportunities, but we need to solve some problems of coordination, of how to orchestrate, the resources and the services here. And so there is research to be done there. So we have discussed these kind of issues in a couple of papers that are mentioned here, and I invite you to read if you're interested. Now, up until recently, satellites were considered difficult to use for communication because even though they had their own market and their own niche, for mobile services, they were too expensive and the terminal would be too energy consuming, and expensive, and so this was not the typical technology you would use for your mobile service. But there have been several developments recently that makes this much more, much closer to what can be done in these scenarios. So from the architecture point of view, we had different types of satellites, like LEOs, but also small nano satellites that much lower cost and can be launched much more easily than traditional satellites. And so this changes the landscape. And so this makes things possible that were not possible before. And from the networking point of view, we have new paradigms like network slicing, network-defined, software-defined networks, network functional virtualization. And so this guarantees improved flexibility, and even more, it allows you to reconfigure your network after satellites have been launched. And so this decouples the installation or the launches of the satellites from how you use them in a networking setting, which makes this paradigm very powerful. I've talked about heterogeneous networks already with different layers of satellites and other nodes. And also batteries, of course, are an issue, especially for drones, for example, because one of the main limitations of drones is the short time you can use them before the battery goes out. And so new battery technology, which guarantees a mission duration of an hour or a few hours, as opposed, will clearly open up new opportunities that will then be very interesting in this scenario. Now, from the antenna point of view, of course, a lot has been done. So both in the physics of antennas as well as in the signal processing area. And so we can now do many things. We can form beams, switch them, change them, move them, track them. We can have multiple beams to cover a broad area with spot beams that guarantee sufficient coverage and signal quality and also rate. So this makes, once again, this type of systems very flexible there. Another advancement is in the use of spectrum. So millimeter waves are being considered. Also, there are some new paradigms like cognitive spectrum usage, trying to coordinate the usage of spectrum by different systems, trying to minimize interference, to make things more efficient, or to be able to reconfigure the usage of spectrum in time. Now, millimeter waves, of course, are attractive from many points of view, but the main question remains, right? And in fact, if you think of satellites where the distance is very large, one may even wonder if this is even feasible, right? Because I told you that at millimeter waves, propagation is more difficult, and so covering large distances becomes very challenging. And so one may wonder, will this even work in a satellite environment where we are talking about hundreds of thousands of kilometers, when in the terrestrial cellular systems we are talking about base stations that cover hundreds of meters at most. And so one first study we did was to just check the feasibility of this. So we took some models developed by the 3GPP on this type of links, where the path loss is the combination of a number of different effects. So the basic path loss is the traditional that we have in terrestrial systems. So freeze equation, where the received power goes as the inverse square of the distance. Then if you have buildings or obstacles, you have some building entry loss. And then we have things that we don't have in terrestrial systems because they don't traverse parts of the atmosphere where this phenomena occur, and also because so far viewed. Okay, so tropospheric and atmospheric absorption. This is how electromagnetic waves at these frequencies interact with the atmosphere, and so they produce physical phenomena that will produce attenuation or signal degradation. Okay, so we incorporate all these effects into our model, and we try to characterize how things work at with different choices. So the different choices we compared were terrestrial system at 2 gigahertz, satellite system at 6 gigahertz, or 28, or 70, or 150 gigahertz. Okay, just to see how things go. Now there are essentially three things related. One is the frequency, I just mentioned. Bandwidth you can use. So as you see from this table, as you go up in frequency, the amount of bandwidth that you can use becomes larger for the reason I was discussing earlier. In the millimeter wave range, you have access to bigger bands, and so you can correspondingly improve your capacity. But of course, as you go up in frequency, your propagation becomes more difficult, your signal quality goes down. But as you go up in frequency, the wavelength becomes smaller, and so you can pack more antennas in a given space. Okay, and so we have three. As we move in frequency, we have three effects. One is the increased attenuation as you go up in frequency. The other is the increased bandwidth, and the other is the increased number of antennas you can pack. And so clearly, the first one, the increased attenuation, is a problem, whereas more antennas and more band are good. And so the question is, since there's a trade-off here, who wins? And so this picture tries to show you the capacity in gigabits per second that can be provided by a system at a frequency in gigahertz given by this axis, with an antenna which has this type of gain, thanks to beamforming. And we have three surfaces here that correspond to three different configurations of the satellites. One is LEO, so 300 kilometers from the Earth. The other is medium Earth orbit, MEO, 10,000 kilometers, or geostationary, 36,000 kilometers. And so you can see that clearly, if you don't do things right, then you go back to this area where you essentially have zero throughput. But if you can have a high enough frequency with a large enough antenna gain, then you can still get gigabits per second or tens of gigabits per second potentially. And so this shows that this concept is actually feasible, even though there are many issues that need to be taken into account. Okay, and just for reference, 50 dB of gain is very easy. 80 dB is entirely possible, and even higher than 80 dB of antenna gain at these frequencies, will be available. If not easily, certainly this is possible. Okay. So we also considered the different architectures where we may have a relay node, because if the satellite is too far from the Earth, so that's distance is one of the main problems, right? So if you can go for a relay system or a multi-hop type of scenario where you have, in this case, a high altitude platform in between, then you can divide distance and you can increase your performance. So if you compare what you can do with a direct LEO to Earth link, which are the solid bars here, with what you can do with the 2-hop through a HAP, which are the striped bars here, you can see that the capacity you can achieve is double or even more than double in some cases. The groups of bars here correspond to different altitudes, so 200 kilometers here and 1200 kilometers there. And the different bars in each group correspond to different elevation angles. So alpha 90 degrees means that you have the satellite right on top of your head, whereas alpha equal 10 degrees means that the satellite is very low over the horizon, which is a more difficult situation. It corresponds to lower performance. Okay. So this shows that the heterogeneous network is actually a good idea and can provide better performance if designed properly compared to more traditional direct satellite type of communications. So, in this scenario, it seems that this non-terrestrial component is very interesting. This is actually being considered not just for public safety, but for many other types of scenarios. And in fact, the non-terrestrial network segment is one of the areas of interest in 6G, and so people are working on that. And so we should expect this three-dimensional component to play a big role in future systems. Open challenges remain, of course, service continuity, because you have many different nodes. If satellites are below Earth, they fly over the Earth quite at some speed, and so you need to manage the constellation. You need to hand over between satellites. Integrating the satellites with the terrestrial component will be a challenge. Latency constraints are there, especially if you're using satellites far from the Earth, because there's a physical limit due to the speed of light, which you cannot beat. And so that needs to be addressed differently. Spectrum coexistence, some of the bands that are being proposed are already used for other systems, and so we need to manage interference. But this is all good material for research. So none of this is dooming, right? This is all source of good ideas and good research that will provide new approaches to make this vision possible. Now, let me switch gears here and address another topic that was a big part of our project, which is end-to-end simulation for public safety scenarios. So why simulation? Well, I'm showing here different possibilities for the evaluation of networks. So mathematical analysis, clearly is very elegant, but doesn't match well complex systems. The other end of the spectrum is live networks, which have the highest level of realism, obviously, because they are the real thing. But they're difficult because they're very expensive. If they are in operation, you may not have the luxury of being able to run experiments because the network needs to do something else, which means make money by serving users. You can't play with it a lot. So you can collect measurements, obviously, but you cannot really play around and make experiments too heavily. And in some cases, these live networks don't even exist, because sometimes we study systems 10 years before they are implemented. So we don't have possibility of having live networks. Testbeds try to implement portions of live networks, but again, they have the issue of cost. And these also may not be available to all groups. So simulation is actually a nice trade-off, but it has to be used carefully, right? So we have been investing a lot in this area of simulation to assess the feasibility of mmWave scenarios, mmWave technology in public safety scenarios, and also in other areas as well. Now, the important thing is that simulation needs to be end-to-end, because sometimes people focus only on this part, which is the radio access part, which is the more interesting one for wireless researchers. But this doesn't tell you the whole story, because the actual experience of the user in terms of service quality and how things go will depend on all the other components as well. And so you have two challenges. One is to include all these parts, so the access network, the core network of the wireless system, the internet, and the server side where the application resides. So the whole thing here, but also the whole stack vertically. So you have to include the application, the transport layer, and then the lower layers that characterize the wireless technology. Unless you do this carefully, then your simulation will not capture the reality. And so a trade-off here is to be able to represent well all this system without being crushed by the complexity and by the running time that this will require when you actually run your simulation. So, making good choices where you have reliable models and accurate models, but with a usable tool that you can actually use to provide interesting results. And if you want to study, some specific scenarios besides, the network infrastructure and all technology, you also need to define the scenarios carefully, and we'll talk more about this in a couple of minutes. Now, our choice was NS3, which is very popular in the academic circles, but not only. Many companies actually use NS3 as a simulator. It simulates at the packet level. It's open source. There is a very large community maintaining and developing it, and it has very advanced models both for the wireless part and for the higher layers, TCP/IP and applications. So at the lower layers, you have all these effects being modeled, propagation models, fading, beamforming, interference, and these all contribute to determining what is the SINR at any given receiver in a certain location. And based on the SINR, there's an error model which generates packet errors. And based on that, the protocol layers will react according to the rules. And so they, the packet starts its life at the application and network layers, and then go down, be subject to all this modeling here, and then hopefully re-emerge on the other side. So we played a role in developing the mmWave simulation models for NS3. So with NYU, we developed the basic mmWave cellular module. And then we also developed a model called the integrated access and backhaul. And then we have been working more recently on vehicle-to-vehicle or vehicle-to-everything type of modules. And all these will be relevant in public safety scenarios. So the basic mmWave module will incorporate LTE ENB, which is what was there before, and its counterpart at 5G, which is called GNB. And also it will incorporate all the lower layers that include the specific mmWave technology for wireless communications. This includes the new frame structure that has been proposed for NR. So this is based on the so-called numerology, which basically tells you how the time frequency blocks are configured, so what is their size and how they are split into smaller pieces. So for example, this type of structure allows you to have a message and a reply within the same subframe, which is 1 millisecond, which is what enables you to achieve a latency over the air interface below 1 millisecond. This is not possible with LTE, which is why LTE cannot achieve 1 millisecond of latency. Okay, so all of this is implemented also along with other techniques like dual connectivity, where you can have LTE and mmWave at the same time, carrier aggregation, where you can join different bands to increase the rate, and so on. Now, IAB this is a concept that's been considered with interest in 3GPP. So basically, not all access points may be connected to the network by wire or by fiber. And this is especially true in public safety scenarios where you may have no mobile nodes that play the role of a base station, but they're not cabled, obviously. And so one thing that you can do is to have a backhaul structure, which is wireless, until you reach the first node, which is connected to the network. And so you combine this radio access links, the green ones here, where users talk to access points, and the backhaul link, which is shown in purple here, which is how you use to go to the cabled base station. And if these two links, the access link and the backhaul link, use the same band, then you have to do interference management and all that. So this is quite interesting. This is also implemented and clearly is very relevant for public safety. And finally, Milikar, which is our module for vehicular communications, where we have, of course, a lot of things that are already there in the traditional mmWave module, but also something that's specific for vehicular communications, like the side link management, the type of interference. So this is specific and enables vehicular communications. Now, the last topic I want to, so these modules, of course, I don't have time to describe, but you have pointers to the papers where you can find all the information. The last thing I wanted to mention was, our work on a library of scenarios. I mentioned earlier that scenarios are important here because they will allow you to get a sense of the actual performance you can achieve. So when we develop a scenario in NS3, we referred to real reports for incidents. So we referred to real situations that happened in the past. And we need to define at least two groups of parameters or descriptors. One is definition of the general elements related to the incident. So what is the incident area? What kind of area it is? Is it buildings? Is it a school? Is it a highway? Is it a industrial plant? Then characterize the first responders. How many of them? What kind of equipment do they have? How they move? And communication requirements. So what kind of applications do they use? Do they use cameras? Do they use which sensors? What kind of requirements their applications need in terms of communication? Okay, so this is defining the requirements essentially and the basic information about the scenario. And then you need to characterize the communication infrastructure. What do we have in terms of communication capabilities? How is the deployment? Do we have a dedicated infrastructure? Is it shared with public network? Is it ad hoc? What kind of radio technology? Is it mmWave? Is it LTE? Is it both? And so we tried to develop three such scenarios. So let me see if I can go through all three of them. So one is multi-vehicle accident. So there's one truck, which is the blue node here, and two cars, red ones. First responders are the dots here, and then we have an LTE macro cell which covers the whole area, and 2 mmWave roadside units. Okay, the application is video streaming, and so the responders want to communicate that. So here's the application layer throughput that can be achieved when the source rate for each responder is this much, 1, 10, or 100 megabits per second, and when the number of responders in the field is 1, 5, or 10. Okay, and the blue bars are when there is only the LTE infrastructure, and the orange one is when there is the LTE plus the mmWave. Okay, so if the source rate is low, 1 megabits per second, then you can see that LTE by itself has enough bandwidth to support essentially everything. regardless of the number of responders. So even with 10 responders, you get, the full, almost the full 10 megabits per second rate here. And adding millimeter wave doesn't help you much because you already have all you need from LTE. Now, if you push your requirements a little bit more, then you see that if the source rate becomes 10 megabits per second, then one responder you can support, 5 also you can support, but 10, you start seeing the limits of LTE, right? Because here you can't really achieve what you want, whereas millimeter wave is able to provide you with this. And this becomes even more visible, obviously, as you expect, when the source rate becomes even higher, 100 megabits per second. So even one responder sees a difference. At 5 and 10, you see a huge difference what you can achieve. So this allows us to measure what kind of infrastructure you would like to have in order to be able to address this kind of scenario. Now, chemical plant explosion. Here we have responders, and also we have a robot remotely controlled that is able to go through the area and collect information, because here, of course, it's a dangerous area. There's chemicals, so there's poison in the air, so you can't send people sometimes in some areas. So the infrastructure is the LTE macro cell and 5 millimeter wave small cells, and the two choices are whether you send the control packet LTE on the millimeter wave band along with the video streams from the responders, or you send these control packets on the dedicated LTE link. And you can see here that mixing traffic on millimeter wave, even though millimeter wave is more capable than LTE, would be a mistake, because the success rate of these control messages, if mixed with the video communication, would be 60% or lower. Whereas if you use LTE, which is less capable technology but more reliable, then you would have 100% delivery rate, which would guarantee that the robot will do the right thing. And finally, there's the high school shooting type of scenario. We have responders, and we have mobile IAB nodes with this concept of wireless backhaul. So the difference between having this wireless backhaul and not having it can be seen here. So if you only rely on the fixed base stations, the orange bars tell you what kind of throughput you have. If you can rely on the mobile wireless IAB nodes, you have this blue performance, which is significantly better, especially when your antenna systems are not very capable. So when your coverage is not very good, having intermediate nodes that relay traffic flexibly becomes a big plus in this. So, more than the specific results I'm showing, I wanted to highlight that, having a well-defined and accurately represented scenario combined with a simulation module that captures realistic behaviors, both from propagation and from higher layers, becomes a key tool in assessing what can be done on, in different situations of interest. And so to conclude, next generation public safety communications could benefit from the features of millimeter wave links, especially the high capacity and the low latency. We offer a research platform that allows us to understand the limits and the opportunities of these scenarios. So, of course, there are many challenges, how to characterize the millimeter wave channel in challenging scenarios, so ground to aerial or in the presence of smoke. How to characterize long-range performance, how to provide robust ad hoc millimeter wave deployments, how to make the hardware more efficient, how to manage multiple layers, multiple technologies in what is inherently multidimensional optimization problem. I put here some references that essentially collect those that appeared during the presentation, and plus some more. on network simulations or other relevant references. Again, this is not a survey, so these references are mostly, if not all of them, from our own work, not because we are the only ones working in this area, but because this is what we presented. And of course, in the papers, you will find references to other people's work, which of course is abundant as well. So with that, I will stop and I will be happy to take any questions.
Sure. Thank you, Michele, for an excellent and timely topic. I know, having worked in the public safety projects, I know how important it is to make it reliable, resilient, and scalable at the same time and provide the right quality of service. I think this is an interesting talk and a lot of research interest out of this I can see. We have few questions over here. I may just ask that. Is that okay, Michele?
Should I stop sharing the screen?
You can stop sharing the screen if you want. It's up to you.
Yeah, unless there are questions that relate to specific slides.
Yeah, you can keep it. Maybe that's yeah. Let me ask. Okay. So first question, Ranjita Bhagwan. There has been a vast amount of work done in ad hoc networks. Can all or some subset of that apply naturally to millimeter wave, or is there a new ad hoc network research necessary now?
Okay, good question. So let me make 2 points about this. One is that most work done on ad hoc network essentially ignored the specifics of the physical layer. So it relied heavily on abstractions of the lower layers and focused on networking algorithms, which gives you the right information to some extent, but fails to capture the effects of in the physical layer, interference, and this becomes more important at millimeter wave, and that's the second point, because at millimeter wave, beam forming and directional communication is key. And as far as I know, there are very few models for ad hoc networks that account for directionality properly by including, so in a way, compared to traditional systems where omnidirectional communication is the norm, at millimeter waves, the weight of physical layer abstractions and good models for the lower layers of the protocol stack becomes much, much more important. And so many of the models used in the past, I expect they will fail because they don't have this capability. So there's a new challenge to include this. Now, if you're able to do that, you can still take inspiration of what was done before, but with this new twist due to millimeter wave technology and directionality of communication.
Thank you. Second question by Uttara Sawant. How would the emergency underwater environments be handled with millimeter wave solution, similar to drones and satellites? Can any complementary infrastructure be used?
You said underwater?
Yes.
Well, underwater, you can't use radio frequencies, or you can only in very, very limited distances. So the technology you use in underwater communications will be completely different, and I don't see millimeter wave as a good match for the characteristics, the physical characteristics of the transmission medium. And so acoustics would be probably better. Optical would be feasible if you have clear water and small distances. But very high frequency electromagnetic waves are not likely to work in this area. So it would be a totally different scenario.
Right. By the way, people who are watching on the YouTube, we may not have access to ask question, but you have the email address of Professor Georgi. You can directly reach out.
Yeah, we'll be happy to.
Yeah, because we have two platforms. Third question on the security related by Rajiv Sori. Any thoughts on the end-to-end security for millimeter wave networks, right? When you're using millimeter wave.
Of course, you can use any security technology you use in other systems here as well, because that happens at the application layer or slightly below. In addition, people claim that since communication is more directional, it becomes harder to intercept and to maybe overhear communications, because instead of broadcasting them all over the place, you are covering only a small fraction of the area. And so that, of course, doesn't guarantee anything in terms of security, but it may make things a little harder in terms of overhearing or eavesdropping type of. But of course, all the security techniques we know for network systems will be applicable here on top of the millimeter-wave technology, which is only at the physical layer.
Thank you, Michele. Another question I have from Abhijit Mandal. It's interesting to see that smartphones can directly communicate with satellites. However, it looked like a smartphone needs to transmit a lot of power, which could be harmful to users. Is there any way to make it safe?
Yeah, so one thing would be to use the two-hop type of scenario where maybe the phone doesn't have to communicate directly with the satellite, but it can send it to maybe a lower node or maybe even a terrestrial node, and then from there you can go to the satellite. So that's one possibility. Another possibility is to use beamforming very heavily, so that you leverage the antenna gain to reduce the transmit power. But this clearly is one challenge, right? I mentioned it clearly that the large distance from satellites will make closing the link with the transmit power we are allowed to use quite difficult, and so the area is open for new ideas or heterogeneous network type of scenarios. But this is clearly one key issue here.
Yeah, so Michele, I may ask one of my favorite questions. I know you have done some work on the handoff on the millimeter wave. I have seen one of your interesting papers. I wanted to understand, with the millimeter wave, we have densification of cells, and now that's going to result into rapid handoffs, right, or frequent handoffs, I should say. How does it affect your upper layer applications? I know you have one or two papers around that. Is there any interesting research going on there?
Yeah. So clearly, you can still use traditional techniques for handoff, but of course, the dynamics is much quicker in this case. One possibility, you may use multi-connectivity. So instead of doing hard handoff, so deciding when to leave a cell and join another, you can keep a living list of cells that are available, so that when you need to move from one to the other, you're already there, essentially. And you can push this even further. So besides having a list of current millimeter wave cells, you may use the concept of dual connectivity across different technologies. And so, for example, you can have LTE as a fallback that can be used both to manage the handoff, so you can prepare the handoff and have all the signaling happen there, but also you could have LTE as a fallback for the data traffic. In fact, if you have both LTE and millimeter wave connected at the same time, you may mitigate the effect of the interruption potentially of the handoff. So there are ways to mitigate these effects related to mobility. Even though I don't think I have not seen a solution which solves all the problems. So this, in fact, I think is still an problem how to manage effectively mobility in millimeter wave systems, precisely because with the densification of the network, handoff will be happening all the time.
Right. Thank you, and that's an interesting area. So I think there's one more question popped up. We are wrapping up with satellite network, core network, and access network in play. How the control plane will be managed? Did you get that, Michele? I think the question is about the control plane. Yeah.
All right.
Yeah. So we have satellite, core network, access network, like terrestrial, non-terrestrial, right? So do you think we need to redesign our control plane anyway? Or I think that is the question, probably.
Well, yeah, I don't think I'm sufficiently familiar with how the control plane is designed now, but one of the open challenges I mentioned is precisely the orchestration of this heterogeneous type of scenario, and of course increasing the number of layers or the possibilities, the technologies available. This will increase the dimensions of the optimization. And so on the one hand, you need to include in the control plane all these other opportunities and manage them accordingly, and your optimization algorithms and decision algorithms will correspondingly become more complex. So that will also add another layer of complexity. But with all this buzz about machine learning and the data-driven approaches, I think complex scenarios like these can be addressed effectively using maybe some of these techniques, learning from data and trying to manage the complexity that way instead of going for traditional optimization techniques.
Thank you. So I'll give a chance to my co-chairs, general co-chairs, Manish Gupta and Ranjita. If you have any specific question to ask directly, please feel free to ask. Manish, Ranjita. I know Ranjita, you have already asked the question. I'll give maybe 15-20 seconds if anybody else has any last question. But this is recorded. It will be available in the YouTube. I know there are some YouTube viewers already there, and this will be available on demand.
If you want, Ashutosh, I can also send you a PDF copy of the slides. Even though from the video they can have them all. But I don't know if there is any way you can make them available. If not, that's fine.
I think you might have already shared that, right?
Yeah, there was a couple of changes I made after I sent you that, so I can send you it again, which is slightly updated compared to what we had yesterday.
Okay, I see. All right. So in that case, let's see. So I'd like to thank the speaker. 1 second, please. Let me just see if I can share this. Can you see my screen, Michele?
Not yet. Yes. Well, it's loading. Yes, I can see it now.
You can see the plaque.
All right, the virtual plaque. Okay.
Yes, virtual plaque. So, Michele, this is a very timely topic. I know COMSNETS, systems, networks, physical layer, everything, you kind of put them together in addition to architecture. Would have been nice to have you in Bangalore. It was a very interesting conference.
I've never visited India, so that would be
right. And so you have to have
an opportunity for my first visit to India.
And the Bangalore section, Bangalore chapter, they also got this Communication Society chapter award this year from Asia Pac, last 2 years, in fact.
And I know many people from the Indian Institute of Science and stuff. So yeah,
right.
Well, there'll be a next time, right?
I know Manish or Ranjita, if you want to say any few words. Otherwise, this is a token of appreciation for your keynote talk at COMSNETS, 13th COMSNET 2021. We'll also have a token of appreciation will be sent to your email address. We can send this to your home address as well.
Yeah, I'd also just like to add, thank you so much, Professor Zorzi. That was a great talk. Thank you so much. And this is not exactly a virtual plug. It will be shipped to your address.
That's right. You see it virtual now, but this is a picture of a real plaque. So I just wanted to make sure. Thank you.
Yeah. So thanks.
All right. Well, thank you all for listening, for inviting me, and I hope you enjoyed the rest of the conference.
Thank you, Michele. Thank you, everybody, for tuning in. I think we should go to the next session. This is the last session, right? Okay, and look forward to the rest of tomorrow and day after. Okay, thank you all.
Okay, great. Thank you. Bye-bye.
Bye now.
Thank you.
Bye-bye.